Okay, so for the third part of this exam, we're trying to show the relationship between the adiabatic saturation temperature and the wet bulb temperature. And over here we have a diagram, and the diagram is showing a tube that is isolated, and we have the mass flow rate of air going in, we have a temperature T1, and the partial pressure of water. And that's what's coming out is T2, which is equal to the temperature of the water. And the saturated partial pressure of water at the temperature of water, or T2. And what we're trying to do here is create an energy balance. So what we're saying here is enthalpy in equals enthalpy out. And in order to start this, we're going to go ahead and write the enthalpy in part of the equation. So we're going to say enthalpy in is going to be the mass flow rate of the air that's going into the tube, m dot air, times lambda, which is the heat of vaporization. And the mass flow rate of air is in kilograms of air per second, while our lambda, the heat of vaporization, is in joules per mole of H2O. And so what we're trying to do here is convert lambda so that it's corresponding with the mass flow rate of air units. And essentially what we're trying to do is find how many moles go into 1 kilogram of air. So we're going to go ahead and erase the units for a second to make it a little bit easier to look at. And multiply lambda, which is the heat of vaporization, by the partial pressure of water that's coming in. So PW, and multiply that by the molecular weight of the water, MW water, divided by RT1, temperature 1 standing for the temperature that everything's going in when considering the pipe. So this part gives us a unit of kg of H2O divided by, so this gives us the units of kg of H2O divided by meters cubed of total, and total being the combination of air and water. And now what we're going to do is multiply again using another conversion unit. So we're going to use the RT times 1, RT1 divided by the partial pressure average times the molecular weight average. And what this does is gives us the meters cubed total divided by kg total. And we're going to go ahead and stop that. And so total again standing for the mixture between air and water. So our second unit conversion is going to be considering meters cubed of the total air and water divided by the kilograms of air and water mixture. And now what we're going to be doing is considering the sensible heat of the air and the water. So what we're going to be doing is saying Cp, the heat capacity, times T 1 minus T ref. And in this case, T ref stands for the reference temperature, and we're just going to say that the reference temperature is 1 for simplicity, 0 for simplicity purposes. So then our enthalpy in equation, if we were to go ahead and erase everything so it doesn't look too cluttered, is going to be this right here. So we're going to be multiplying the mass flow rate of air by lambda, which is the heat of vaporization or vaporization, times the partial pressure of water times the molecular weight of the water, divided by R, which is gas constant, or just constant, times the inlet temperature. And that's going to be multiplied by R, which is another constant, times the temperature, divided by the average partial pressure of the air and water, and multiplied by the average molecular weight of air and water. And then we're going to be adding the heat capacity times the temperature, since our reference temperature is 0. So now what we're going to be doing is going ahead and looking at enthalpy out. So now since we have solved our enthalpy in part of our energy balance, now we're going to be looking at enthalpy out. And in order to do that, we're going to be considering the mass flow rate of air multiplied by the heat capacity, which can be multiplied by the temperature out. And we're going to be adding the heat of vaporization to it. And since we're adding the heat of vaporization to keep the units uniform and in agreement, we're going to be using unit conversion to convert back to in terms of air. So since this is going to be in terms of the heat of vaporization is going to be in terms of water, we're going to say that the saturated partial pressure of water at TW times the molecular weight of water divided by the partial pressure total times the average molecular weight. And then we're going to be multiplying the RT at top and bottom. So this is going to be our enthalpy out equation. And now we can go ahead and begin to cancel things to simplify our energy balance. So right off the bat, we cancel out M air on both equations. Then in each equation respectively, we can cancel out RT. And now what we're going to be doing is looking specifically at the lambda heat of vaporization portion of each equation and start to simplify things. So what we're going to do is keep lambda, the molecular weight of water, and the total partial pressure, and the average molecular weight, outside of the parentheses because those are kind of constants in a way. And then what we're going to do here is, since it's going to be enthalpy in minus enthalpy out, we're going to have PW minus PW. So what we have done here is said the partial pressure of water minus the saturated partial pressure of water at the temperature of the water is going to be equal to and multiplied by the heat of vaporization, which can be multiplied by the molecular weight of water, all divided by the total partial pressure times the molecular weight of the averages is going to be equal to the heat capacity, T2 minus T1. So we took into consideration the heat capacity and the heat of vaporization parts of both enthalpy and enthalpy out to get this simplified version of our equation. So in order to show the relationship between the adiabatic saturation temperature and the wet bulb temperature, we have to recall the equation that we created in part A2 of this exam for the wet bulb temperature, which is going to be the molecular weight of water times the heat of vaporization times the partial pressure of water at the surface minus the partial pressure of water and the air equal to the total partial pressure times the heat capacity times T2 minus T1. And we can see here that these two equations are very similar to one another. And basically what is going to be occurring is that the temperature that we read from the wet bulb equation is going to be the same temperature that we read from the adiabatic saturation temperature equation. So that's the relationship between the adiabatic saturation temperature and the wet bulb temperature.